So part of the screen is blocked again. Oh yeah, I see it now. What does it do that? Is it better? Is it okay now? Yeah, okay. Okay, to the person who's asking a question now, I will look this up. I need to talk to Lidia, and I didn't see what she did in the tutorial. Okay. All right, so then let's start. Please tell me again if some part of the screen gets blocked again. Somehow it has to do with what windows I have open on the laptop. I don't know. Okay, so the good news is that the lecture notes for this lecture are online now on Moodle. You should be able to download them. The quality is a bit different because I got a little home scanner. And now it just arrived today. So after today's lecture, I should be able to upload all the other lecture notes from the previous ones. Yeah. So please ask questions either in the chat or unmute yourself and ask. Today, we will continue talking about angular momentum, and this time we'll finally talk about the central potentials that we saw, of which an example is the hydrogen atom. So I think today we only have time to maybe start introducing the problem of the hydrogen atom. There'll be a question at the end, which is that at some point we'll end up with like this huge differential equation for the hydrogen atom. And the question is whether you want me to derive it explicitly in the lecture next week, or if we just talk about the main insights. So last year I only talked about the main insights. The whole derivation is a bit long. So the way we'll do it is, if I receive more than 3 emails saying that they want to do it, then I'll do it in a lecture. Otherwise, I won't. Okay? So send emails until Monday if you really want it. And we'll see what this is in a bit. Okay. So what did you do last time? And you did it again now. It was to find these explicit expressions for how all these angular momentum operators act on the wave function in spherical coordinates, right? And then for simultaneous eigenstates of LZ and L square, we have the equation LM, which is the eigenvalue equation, right, for both of them. And here we got it just like in spin, LM. And then we even derived an explicit form for this, for the wave function of this eigenstates, which was this, R theta phi. And we saw we can decouple it into some R of R, which we don't know yet. But the idea is that it does not affect the eigenvalue. Could be anything for now. And then some function that depends on L and M of the 2 angles, right? And we even broke this down. So this function y is called the spherical harmonics, and then we broke it down in the part that depends on this angle phi, and the part that depends just on theta, right? These were these polynomials that we know how to compute. We know the bottom, you know how to go up using these ladder operators. So we know how to compute them. It's not pretty, but we know how to do it. This is very easy to compute, and this is free. So one thing is that if you get a different function here, you have the same eigenvalues for M and L, but but the function itself is different, which means that the state itself is different, right? So you can even do a small correction here and say, well, this is ML and something else, which depends on this function there, but does not affect these eigenvalues, right? Just like we saw for when we first talked about generalized spin, that there could be, that there are aspects of the eigenstates that affect the eigenvalues, and then there's some degeneracy, right? That there's something else. And this will be useful now when we talk about specific potentials, because then we'll see that it depends actually on here. Good. So here we could also have like alpha. Okay, good. So now we're going to restrict ourselves to this central potentials. What I mean by this is that if we have our Hamiltonian, you have the kinetic energy as usual, talking just one particle for now, plus V of R. What does this mean? Well, just like before when we had V of X, it means it only depends on this coordinate R in spherical coordinates. So what this means is that by V of R, if I expand it in spherical coordinates, it's going to have some V of R times the projector into this position R, this radius R, and then it does nothing on the other two coordinates. Oh, phi. Good. So just to see how does it act on the wave function, in spherical coordinates. So let me just write it like this. The action, so V of R, it takes this to the same wave function. It's just like for the usual potential that we talked about, multiplied by V of small r, right? So now it corresponds to this R here. And we can prove this if you'd like. So I'll just write here because, we have the state psi, which you can expand like we saw. I just use a different letter here. D theta, D phi. Here's the wave function. Then we have these three kets, right? Each on their own subsystem. And then when we apply V of big R on this stage, what we get is now, okay, the R. Now come all of these again, so I'll just copy and paste, it's a bit faster. Juk. Now comes, well, this is just a number. So the wave function, no, that's not what I meant. Okay, I'll just write it by hand. The wave function is just a number again. Now comes the V of small r. And let me use here special variable r. And now comes chuk. Right. And this thing here, well, this is a number again. It's just a delta function between r and r prime, which means we can get rid of one of the integrals. Say we get rid of the r prime integral. So we end up with the r d theta define v of r, and then okay, right, and this is what happened to the wave function in the end. And the integrals, you know, they go like from 0 to infinity, 0 to pi, 0 to 2 pi, and so on everywhere. Okay, so this is one part of the Hamiltonian. We want to know how the Hamiltonian acts on the wave function in spherical coordinates, because we're not going to transform this to Cartesian coordinates. So now we're left with this part. So again, what is this? Well, we know it's in Cartesian coordinates, right? Z plus, we have here the p y squared. That's right. Identity in Z plus okay. Right, so we could try to transform the whole operator to spherical coordinates. Maybe it's fun to do, I don't know. What we can see is, like we did for the angular momentum, we see how this one acts on the wave function, and then we transform this action to spherical coordinates, right? So we saw that this is a definition, but we know that p squared acts on the wave function in Cartesian coordinates to s minus h square, and then a bunch of derivatives. Right, this is a Laplacian. So now what we have to do, this is called Laplacian, right? You probably saw it in calculus. So what we have to do is just translate all these derivatives to spherical coordinates. And it's exactly the same procedure as we did now in the tutorial for the other ones. Because it's the Laplacian, it's a very standard thing. You probably did it already in your calculus lectures. So we will not do it here again. I'll just give you the solution. Okay, and let me try not to make any mistakes. It looks a bit terrible, but we'll see that we can simplify it very nicely. So it takes the spherical wave function to the following minus h bar squared. And now that's this whole thing. Squared ddr squared. I'll not write all the coordinates here, so it's just, this is again the wave function, plus 1 over r squared. And now comes 1 over sine of theta. Theta. The theta. Plus 1 over sine squared of theta. D squared d phi squared of the wave function. Okay, now this is pretty horrible, but it should give you like a deja vu feeling, because we've seen something like this before. So in fact, this here looks a lot like the action of the angular momentum on the spherical wave function. So I'll grab it in a bit. So this is minus 1 over h bar squared, the total angular momentum acting on the wave function. Oh. Okay, so let's go look for it. I know we did it. Oh, there it is. Right, so here it is. As you see, There it was, right? So up to the minus sign and this h bar constant, what's inside here should be exactly what's inside there. So this will make our life much, much easier. Meaning what? So we can just simplify this, this p squared with having here this L squared. And now if we bring it together with the whole Hamiltonian, we get the following. So we get that the Hamiltonian applied on the wave function, it takes the wave function to the following thing. So on the one hand, we have this. Remember, we divided the momentum by 2 mu chuk of r squared r plus 1/2 mu r squared. So the h bars cancel each other out. Here comes this, the angular momentum applied on the wave function. And now plus the potential that we still left behind, which we saw that when it's applied on the wave function, it's just right. So remember that it's always the wave function at r, theta, and phi. I just don't write it all the time. Okay. So from here, we have some good news, right? So all of this only depends in r. This depends in r. This depends in r. Nothing depends on the two angles, except this factor here, L squared, right? And L squared commutes with L squared, and L squared commutes with LZ. So from here, the conclusion is that the Hamiltonian commutes with L squared, and it also commutes with LZ. If you want to do it like properly, not just by looking at it, so you can look at it and say, well, L squared and LZ don't depend on R. The Hamiltonian parts that don't depend just on R are L squared, so everything commutes. If you want to do it properly, you can think of it of like, oh, if I know how the Hamiltonian acts on the wave function like this, I can think, well, this and this is like an operator that acts on, that is only in the R subsystem, then acting on the state. So I'll show you what I mean by this. You can say, well, the operator is going to be just some R, that some part A that acts only on R and does nothing on the other two. Right? That's this part and that part. Plus, well, we have here, you could think of it as two parts. So first, I have something that acts on R only, on theta, on chuk, multiplied by this L square, and the L square we also say, well, it doesn't act on R, it's just some L square that acts on theta and on phi. Right, this is one way to do it. And then if you simplify this, if you multiply these two things, then you get just B on R tensor this L squared on theta and phi, right? So we can do this and then say, well, you know, then this obviously commutes with LZ, because then LZ, you can also write it as, oh, nothing happens on R, but something happens on theta, theta and phi, and L squared, same thing, right? Nothing happens on R, but something happens on theta and phi, right? And from here, you can see already that they commute. But, you know, in practice, people just look at it and say, oh, it doesn't depend on the angle, so they commit. So why is this good? This is good because now we know that they share a basis of eigenstates, right? So if they commute, then the eigenstates of Lz and L squared are also eigenstates of H. So this is great. So now what we have is that we have 3 equations for eigenstates. So we have H, Lm, and let me put here already this alpha, this degeneracy that we didn't know before, equals E Lm alpha. And then we have the other 2, right? We have Lz Lm alpha. And the energy is allowed to depend on this alpha now, right? That's what was missing. And L squared, Lm alpha is H bar squared L plus 1 Lm alpha, right? So now I have these 3 equations. And you know, we even know the form of the wave functions, which is that this Lm, and let's put here the alpha, equals R. R we saw does not depend on L, but can depend, sorry, does not depend on M. We saw this last time, right? Because when we act with ladder operators, it doesn't change this function, but it can depend on L and this unknown thing alpha. And then we have this thing. So this is on R. Okay. So now our focus is going to be to try to work out what this is, because now our Hamiltonian does depend on R, so it will give some constraints on what these functions can be, right? So we'll investigate these things. So it will turn out that for the specific case of the Aerogen atom, this alpha is going to be a number that's a natural number that is, it must take only discrete values. So instead of alpha, it's going to be n, okay? And it's not like this for every central potential, but for many of them, this alpha turns out to be a discrete number. So we're just going to call it L. And yeah. Just by calling it n, we're not imposing that it must be discrete, right? So it could still be anything. Okay, so now we need to apply the eigenstate equation, the Schrödinger equation for energy eigenstates, if you want to find out more about this thing here, right? So we do it, and it will be simplified. So we start with the first one. So we know that the Hamiltonian applied on the function of, say, NLM this must be the energy eigenvalue. We can write, let's not write n for now. Let's just write E Zurich and Lm of R theta Zurich. Okay, so we know the expression for the thing on the left. We'll leave the thing on the right as it is. And now we go get what we did before. There we go. Yeah, I understand now that it's much easier to follow if you have the other notes, because I'm always going back and forth. Okay, so we have this, right? And now what is the good news is that now this applies just to write all the subscripts, is that we know this thing here, right? Because now we're talking about eigenstates, so we know that this is going to be just h bar squared L plus 1 n. Okay. We also know that this thing is going to be some r that depends on n and l tensor, times something that depends only on the angles. And if you put it like, for example, here, this part that depends only on the angles is not affected at all by all these derivatives. So you can just put it on the back. So then you have the function here, the function here, the function here, the function there. So you can kind of cut them all out. If it's never zero, which it's not going to be. Yeah, things are well behaved. Don't worry about this. Okay, so then we can simplify this a lot. And what we get is this. So we get this minus h bar squared 2 mu r squared ddr r squared. And so again, because nothing happened to this y part, we get here just the r. And then on the right, it's all kind of constants times the thing. So we put it here. So here is going to be the r, l, and n of r. And then what's left here is going to be the energy minus. And now we have this part here. That's h bar squared l plus 1 2 mu 1 over r squared plus this v of r, which could still be anything, right? We've not done anything to it. Okay. We are going to simplify this even more. I mean, note that we're very invested in this because we want to explain the behavior of molecules and atoms and so on. So people would be very, very invested and would not be demotivated by this horrible expression. So what we do, first of all, we're just going to call this, there was a minus sign there. Minus. So this whole part here, minus 1 minus the other, we call it the effective potential, right? It's again a function that depends only on r, but of course now it depends also on l. Okay. And then on this part, we have something pretty terrible. So what we'll do is we're going to simplify it by defining a new function, and I'll tell you in a bit. We're going to define a new function, which is just the radius multiplied by this, which we'll see will simplify this part on the left a lot. Okay. Why is that? Because if we have now all of this part that was on the left, well, up to this, let's say like this. This turns out to be just 1 over r t squared t r squared. There's a typo on the lecture notes here. It should be r squared of my function r. Yeah. It's a very easy thing to prove. You'll prove it in a tutorial next week. Yeah. Just take this derivative and see that you get what's on the left. And what was the VF? Let's just recap what the V effective is of L. This is our original potential plus this term that depends on 1 over r squared. Did I forget anything? No, that's it. Okay. So it's So you can think of it, well, I'll show you how we can think of it. So now we simplify this whole equation that we had before and becomes very nice. So you have minus h bar squared over 2 mu. Now this thing that was here of my function equals ENL minus V effective R times UNL of R over R, but because I just replaced where the, maybe I go back and show you. So because we define UNL like this, then R is going to be UNL over R, and this whole thing we simplified it on the right, so it's a bit more treatable. Okay, it looks like this. Now we say for when R equals 0, this potential is going to diverge very quickly, right? It goes to plus infinity very quickly, unless this exactly cancels it out. It's not going to happen. It doesn't happen in most physical situations. So this thing is going to be infinite. When the potential is infinite, the wave function is 0. Even the wave function times R is going to be 0 in this case. So I'll just write here, R equals 0. We don't worry about, because in this case, R. For R larger than 0, we can cancel out these things, right? On the left and on the right. It should only be a problem when R is 0, but we took care of this separately. So now we have a differential equation that should be now very familiar. So here's E, whatever difference on N and L. No, I'll just write E minus V effective of L R. So why is this familiar? Because this is exactly the same equation as we had when we were talking about states in 1D and stationary states in 1D, right? If you had the Schrödinger equation in one dimension with just some potential that depended on just a variable x, then this was exactly the Schrödinger equation for stationary states. Let me just recap what this is. So remember, in 1D, when we had h equals p squared 2 plus v of x, then the equation for the wave function was exactly, so we have p squared over 2 mu plus v of x. At the level of states, it still look like this. Right, and then at the level of the wave function, it was exactly this, right? The momentum just gave this h bar and the second derivative in order of x, because we have only one dimension, and then the vx we could take to the other side, and it was E minus vx. So let me just, I'll bring back the other one so we can compare it. So this is the one we have now. Okay, this is the one we have now for the spherical coordinates and the central potential. And this is the one for the one dimension, right? So it's exactly the same equation, so it has exactly the same solutions. And we saw how to solve this one. Well, I mean, we saw how to solve it for the case of constant Vx. And now the difference is that our potential here is going to be very complicated, right? It has this this part that depends on r square, 1 over r square, and then it still has the actual potential that is also going to be complicated. Okay. So now, how to solve it and how to find the exact solutions, it will depend on the form of the potential, right? So now we look at one specific potential. And this is going to be now the famous hydrogen atom. So what's the idea of the hydrogen atom is that, so there's a proton in the center, and then around it, there's an electron. It's not stopping there. It's going to be a wave function like this wave functions that we will compute, but that we saw already a bit before around it. And the force that they feel between each other, among other things, is going to be, the main thing is going to be the electric force. Okay, so just an electric interaction. And the approximation that we're going to use, so the atom is 3 to 4 orders, sorry, the proton is much bigger than the electron. It's like 3 to 4 orders of magnitudes heavier. I put the exact constants in the lecture notes if you want to look at them. But the idea, and they have the same charge, just with different signs. So the idea that the approximation that we're going to make is that the proton is sitting in the middle, and you're just going to compute the effect of this electric force on the electron, and not the other way around. So it's the same way that if you want to solve the equations for the solar system, we can, it's a good approximation to say, well, the sun is quiet in the middle, and then we just compute the effect of the gravitational force caused by the sun on the planets that are much, much smaller, much, much lighter than the sun, right? Of course, if you want to be super, super precise, there's also a back effect of the planets on the sun. But, because it's so much heavier, it will really change very little at the end. Okay? So that's our approximation. Let's just write it down. So because the mass of this proton is much, much larger than the mass of the electron, then we think of the proton as something that is sitting there as just part of the system. So we neglect the effect of the electron on the proton. Yep. But they have the same charge, so then we can compute the potential felt by the electron. So now all we're thinking of the atom, we're thinking just of the electron, right? This is our particle that we care about. So what is this given by? In the electrical case, this is a constant, and then it's given by the mass of the first particle, the charge of the first particle, the charge of the second one, divided by the distance between them. And Q the electron, the charge of the electron is -1 electron charge, and of the proton is going to be plus this. So this is a number that is 1.6 times 10 to minus 10, and coulombs is just the international system unit. So what matters is that they have different signs. So this is minus k e squared r squared. So this would be now the potential that we need to plug into here, right? So now we have that V effective is that term that depends with 1 over r squared, and now we have another term that depends with 1 over r. And so maybe I'll just write this explicitly. So V effective of L of r is minus k e squared over r squared plus what was it? H bar squared 2 mu L plus 1 over r squared. Sorry, this one is not squared. Okay. right? So now the differential equation that we have to solve is this one here, which looks innocent enough, but now this potential has this terrible form. Now, this is solvable, and it's about, as I said many times, it's about like as far as we can go with analytic solutions for this kind of Schrödinger equations. And if you want, this is the thing, if you want, we can do it explicitly in a lecture. If you don't want, it's in chapter 16 of the book. This is the Schumacher-Westmoreland book. There's a link on Moodle. And you can see there how it's done step by step. There's, what they do is then to look at some limits of this equation for small r, for large r, and so on. And there's one important conceptual insight that comes from there. And that's the fact that from solving that differential equation, we find out that the energy is quantized. It's a similar thing like when we did for the angular momentum, for the spin, we saw that S can only take integer or half integer values, and M the same thing. Otherwise, you'd get unphysical solutions. So it's exactly the same here. Same approach, let's say. So I'll just tell you now what the main insights are. And now you tell me if you want to see the derivation explicitly. It will not be in the examiner. So the energy is quantized and depends on a number n, which is minus mu k squared e squared over 2 h bar squared, 1 over n squared. And what values do we get for n? So it must be larger than L. Okay, so it's a natural number. This comes from solving the differential equations, and we see that for anything else, you get solutions that diverge, that are otherwise unphysical. So this tells us what? Well, we have n must be larger than L, and this is larger than M. The energy depends only on n. So we have now these three different quantum numbers. They all, and absolute value. So they're all things. Which means what? Well, if I now plot, for example, L and N, right? So now we have many options for energy, for stationary states of the hydrogen atom. So when L equals 0, N equals 1, there's only one state, right? Which says what? Because M must be 0. When N equals 2, then L can be 1 or it can be 2. So it can be, it can be 0 or it can be 1. So we have here and here. Whereas here we have three possibilities for states. So we have M can be -1, 0, or 1. And so on. So if you have here 3, we can have this detector. And the energy goes up here. Well, 1 over square root of the energy goes up like this, right? So the energy of each eigenstate depends only on the n. Now, these things are important, for example, in chemistry, because it's different states correspond to different, different properties of materials that you get later, because then we can also try to generalize this to different atoms that have more electrons or more protons or so on. And just so you know, in case you see it later, in chemistry, there's some notation where it depends on the total angular momentum. So these are called the s orbitals. These are the p orbitals. These are the d orbitals, the f orbitals. So if you've seen this, if you ever took a chemistry course, if you've seen this, before, that's kind of what it means. So for example, if I have, if someone says we have an electron in the 2s orbital, what this means is the state of n equals 2, L equals 0, M equals 0. Or if they say something 3p orbital, this means n equals 3, L equals 1, and M, there's still several options here, right? So if you see this in chemistry popping up a lot, it comes from here. Good. We just from here, we will be able to do, and we'll do this next time, we'll compute some properties of the atom that we don't know. For example, what is the size of the atom? What's the average radius of this electron when it's in one of these stationary states? And we'll try to look at other more fun properties that we can compute. But if you want to see the whole derivation of this and also of the exact with functions, then please let me know. Otherwise, we will move on. After wrapping up the Aerogen Atom, we will move on to modeling uncertainty in quantum mechanics, which is more fun for me. All right, so with this, if you have not had lunch during the lecture, then I wish you a good lunch. See you next week. And I'm here if you have questions.